All right, here is our penultimate lesson on our log unit, second to last. We're going to talk about properties of logs. This says to get your book out and read about it. I want us to think about it, though, because I don't think we need to look these up. First of all, you've already learned all these properties, but you might not remember which one goes with which, bless you. But if you remember the one key thing about logs that we talked about, I know it's been a while, last Tuesday. What was like the big thing about logs? Logs are what? Logs are exponents. If you can remember that logs are exponents, then that's going to help you understand what's going on with each of these things. So we're going to we'll do these properties, but while we're at it, let's go ahead and talk about properties of exponents too. Properties of exponents. All right. So what's going on in this situation is I've got a base. It's going to be a common base, and there's some multiplication going on inside of the log. Okay. So I want you to think about what this is going to be. This is going to be like if I've got a base, and one of them's I'm using lowercase letters here. One of them's to the r power, and I'm going to multiply that with the same base, but to a different power. Do you remember with exponents, what do we do with those two exponents in that situation where we're multiplying? What do you do with the exponents? You add them. That would just be b to the r plus s. We're adding the two exponents together here, right? Well, remember, logs are exponents. So if we're adding two exponents, then we're going to be adding two logs. So this is going to be the log base b of r plus the log base b of s. So we know when we add exponents when we're multiplying. So can you kind of see the connection between multiplication and addition here as well? It's the same rule, just in log format. All right, this one has division here, kind of the same idea. If I had a base b with an exponent of r, and then I was dividing it by the same base with a different exponent, what would we do with those two exponents in this case? We subtract them. It would be r minus s. So in the case where we have a log with division on the inside, then we want to be subtracting our two exponents and subtracting our two logs. So this would be log base b of r minus the log base b of s. All right, so this one's kind of a little bit harder for me to kind of make a connection. But what I see here is I've got a base, and then there's an additional exponent going on here. So this would be a situation where I've got b to an exponent, and then that is being raised to another exponent. So that's that kind of power to a power situation. In that case, we multiply the two exponents, right? So we're going to be multiplying two exponents here. One of them is going to be c, and the other one's going to be the log. For me, this is more of a visual thing. Did you guys learn it this way too? You take that c and you bring it down in front of the log. That's kind of how I think of it. If you have an exponent inside of a log, then you can turn that exponent into a coefficient. This is what exponent would I put onto any base to make it equal to 1 rule. So if I had a base and I needed to put an exponent on it to make it equal to 1, what's that exponent got to be? What's the thing you can put onto any base and make it equal to 1? 0. Well, any base except for 0. So remember, the log is the exponent. So what is the log of 1? No matter what the base is, what is the exponent? 0. So remember, a log is an exponent. It is the exponent I put onto a b to make it equal to 1, which is 0. I don't think we've talked about this yet. We've got time today. Do you guys know what 0 to the 0th power is? Ooh, is it 0 or is it 1? What's the pattern say? What's 3 to the 0? And 2 to the 0 is 1, and 1 to the 0 is 1, so 0 to the 0 should be 1, right? So it follows the pattern. Except there's a different pattern. What's 0 to the 3rd power? What's 0 squared? And 0 to the 1st is, so then 0 to the 0 should be 0. Ooh, we hate when this happens in math. Like, it's inconsistent, right? So what do? We cry. No. Well, kind of. It's like the mathematical equivalent of crying. We just hide it away. We sweep it under the rug and we pretend it doesn't exist. We're like, nah, that's just not there. It's undefined. Undefined literally means like we don't know, so we're just gonna ignore its presence. It's not part of math. All right, so 0 to the 0th that's the one thing you can't put an exponent on 0 to make it a 1. Or maybe you can, we're just not sure. So we say it doesn't exist. All right. It says stop and think about how they're related to rules for exponents. We did that. We totally did that. Okay, let's do some problems. So here we go. In this problem, we're going to write this as a sum of logs or multiples of logs. And when we do this, we do not want to have any exponents or square roots inside. So let's see what we can do here. How many things do you see being multiplied together inside of this log? 3 things. So when we write our answer, it's going to have 3 logs. We're going to have a log of 8, and a log of x, and a log of y to the 4th. And the question is, what are we doing in between them? Inside of the log, we were multiplying, which means what do we do to exponents when we're multiplying? We add the exponents. Logs are exponents, so they follow the same rule. And we're going to go one step further just to clean this up. When we do this, typically we do not want exponents inside of a log. So we'll bring that exponent to the outside. My final answer would be log of 8 plus log of 10, or sorry, log of x plus 4 log y. All right, what do you see going on inside of our log here? Just as a quick reminder, though, before we get into this, because this question came up first period, what's the base on this log? Base of e, right? This one has a base of 10. If it's not written, we say it's a 10, but when it's an ln, that's a log of e. Okay. Anyways, I see kind of 2 big pieces being divided in there. Do you see division? So we must be talking about 2 different logs, 2 different ln's, and this time they're going to be subtracted. So one of the things being divided is the square root of x squared plus 5, and the other one is x. Is there anything more we can do to that? What if I wrote that first log, instead of it being a square root, how can we rewrite a square root as a power? What power would it be? Half, yeah. And then what could we do with that 1/2? Maybe you bring it down front. Ooh, and then that gets us to here where we've got addition inside of the log. What do the rules tell us to do when you've got addition inside of a log? Then what do you do? Addition on the inside translates into... Is that how that works? Multiplication on the inside translates to addition on the outside. That does not work in reverse, though. Sorry, that was a trick question. That's a mean thing to do on a Monday when you guys are still halfway in a turkey coma. There is no rule for when there's addition on the inside. There's no rule. Can't do anything with it. We're just going to have to leave it like that. The only thing we could do is if I could find a way to factor this so that it was two things being multiplied together, then we could split it up and turn that into addition on the outside. But right now, with addition on the inside, there's nothing that we can do with that. So just have to leave it. That's as good as we can do on this one. Any questions on those first two? All right. This one's different. They want us to write this as a single log. As a single log. So we're going to try and write this as a single logarithm. And I'll tell you that the one thing that's blocking on my way right now is this 2. We can't combine logs that have coefficients. Okay? Unless they have the same coefficient, you could factor them out. But in general, you should always get rid of coefficients first. I'm just going to write that down since this is our notes. So get rid of coefficients before combining. That's not a big deal. We know what we can do with a 2. If it's a coefficient, it can pop up here and become an exponent. So let's rewrite this first without coefficients. And then we can combine these two things into a single log. Since it's subtraction on the outside translates to division on the inside. Go ahead and write that down and then simplify it. That fraction simplifies, doesn't it? You got x's in the top and x's in the bottom. We could do some canceling. Maybe do something with this square first. So far, is this looking kind of familiar from last year? You guys did some work with properties of logs. We want to be familiar with this for next year because you'll be dealing with expressions with logs. And if you can ever take something like this and turn it into a single log, it's just going to make your life easier. Especially with ln's. I told you guys that E is super, super special in calculus. You're going to love E when you get to calculus. Do you guys want to know why E is so special? Yes? Are you interested? Let me just show you this one thing really quick, okay? Let me show you this one thing. You've got your graphing calculator. This may be helpful. Because this is so cool. And then I hope this is a little bit of a spoiler for next year, but that's okay. Chances are you'll forget it before that anyways, but this is so cool. So get your calculator and graph e to the x power. Graph me e to the x power and do it on let's set our window back to zoom, standard zoom level. Do you guys remember how to do that? Zoom 6. Boom, there it is. So about half of calculus About half of calculus, and I'm hoping, again, this is a little bit of a spoiler, but about half of calculus is the idea that for a curve, you can find the slope of a curve, but only at a particular point. Like, so if I were talking about this point right here on my curve, and if I drew a line that was tangent to the curve at that point, you see how that line is like just touching the curve just in that one place? Then the slope of this tangent line would be what's called the derivative of this curve at this point. To me, it looks like it's about 1, up 1 over 1. What do you suppose the derivative of this curve would be right here at that point? What does the slope of that line look like? What's the slope of a flat line? 0. So yeah, the slope of this line would be 0. The slope of the curve at this point would also be 0. If I found this point here, if I drew a line that was tangent right there, it's going to be some kind of negative slope right there, right? So that's why we spend so much time in pre-calc talking about increasing and decreasing, and that's also why they call these things turning points, because it's where the slope turns from a positive to a negative. So calculus is really like the first half of calculus is all about like, can you find the slope of these different functions at these different points, right? The cool thing about E is the slope at any given point on the function is the function itself. So if I wanted to find the slope at 0, the slope would be equal to, and this doesn't work for any other function except for e to the x, the slope would be equal to e to the 0th power, which is 1. Okay? If I wanted to find the slope right here at 1, it's going to be some positive slope, agreed? The slope at 1 right here would be e to the first power, which is whatever e is, 2.7 something. So when you go to find the derivative of e, the derivative of e is e. E is its own slope. So the graph of e also tells you exactly what the slope of every point on that graph is. It also tells you the area underneath the curve up to that point. I don't want to get into all that stuff, but it is super special in terms of calculus because you're gonna first learn all these rules about taking polynomials and finding derivatives for them, and then they're gonna be like, and then there's e, and to find the derivative of e, the answer is e. It is its own derivative, which is awesome. Anyways, okay, enough of that. For right now, I need you to know that ln goes with e and that e is very, very special. All right, let's flip over. Actually, I'm going to do one more, but let's flip over in the back where we've got a little bit of room. Down at the bottom of the page, a little bit of space here. We came up with a really good one first period. I'm just going to do the exact same one because it was perfect. I want to give you a problem that I remember causing some issues on a test a couple of years ago. I don't know if this is on last year's test or not. So it's kind of like the last one we did where we're trying to split things up into multiple logs. This is interesting because it has both multiplication and division in it. See what you can do with this problem. There is a super common mistake with this. If you're not sure what to do first, when I look at this problem, I notice the division first. That's kind of the biggest thing that's going on. There's multiplication happening inside of the division, but I would deal with that division first. So my first step would be to rewrite this as a log of two things with a subtraction in between it. That'd be my first step. And then from there, those two logs can get expanded further. And eventually you'll have some exponents that you can deal with also. But I'll let you do that on your own. See what you can do with that. Give it a try. meant for that to be a 2. I usually cross my z's because my z's and my 2's end up looking so similar to one another. If you're looking at my screen and thinking you made a mistake, don't erase because there's a mistake on the screen. So I was just waiting for a few more people to finish up. If you get finished, I would love for you to see if you can spot the mistake that I have made on the screen. Oh, it's such a common one, and it's really easy to do too. Anybody seeing it? Did anybody write the same thing as me? Yay, good. Hey, it's my favorite mistake with this problem. It's a good one. And then once you see why it's a mistake, then you don't have to worry about making it again. That's what I believe. Make every mistake one time and learn from it, and you don't ever have to make it again, right? So where is it? Where's the issue? Help me out here. Mm-hmm. This should be a minus. Agreed. Or there's another way I could fix this. So yeah, so I agree. So the way I look at it is, didn't these two things come from the same log? And the entire log was being subtracted, right? So I should probably keep them grouped together when I split them up to make sure that both of them are being subtracted and not just the first one. Does that make sense? And then with that ends us back at the same thing that you just said a second ago, right? You told me that this plus should be a minus. If I were to distribute that negative, that would make it in there. Yeah, so my final answer, I would probably write that as a minus, and then I'd also get rid of the exponents, everything. So final answer, natural log of 2 plus 3 times natural log of x minus ln y, and then minus 2 ln z. Is that what you guys were able to come up with? I had a student several years ago who came up with a rule for this. They said, if you've got a fraction with a bunch of multiplication and division, this, by the way, this only works with multiplication and division. If you throw pluses and minuses in, this goes out the window. But she said, if you've got a fraction inside of a log with only multiplication and division, everything on the top of the fraction is going to be a positive log. Everything on the bottom of the fraction is going to be a negative log. I was like, is that 100% true all the time? And then we messed around and she fixed it and she said, only if all the exponents are positive to begin with. But her explanation was this, and I thought this was very clever. This is the same thing. If I wanted to write this without division, could I not write it as 2x to the third, y to the negative 1, z to the negative 2? Isn't that the same thing? Yeah, and then it's a lot clearer to see why this is going to end up with a negative coefficient. This one's also going to have a negative coefficient, right? Because we're going to end up pulling both those negatives down in front. All right. You guys are awesome. Any questions about that stuff? Okay, we're going to do something out of the book. If you don't have your book with you, that's fine. I'll put it up on the screen. There are going to be 8 relationships that I'll put up on the screen, and your job is to sort them into true ones and false ones. There are 4 of each. I really like this exploration in the book because it exposes some very common misconceptions about logs, some common mistakes that a lot of folks make. If I can actually find it, here we go. And I'll zoom in to get you a little bit better view of that. So 8 equations. Some of these equations are true, some of them are false. If you could just recopy those 8 equations over into those 2 columns on your packet. We'll come back together and chat about these in just a minute. Let me know if you've got questions on these. Basically, I want you to be comparing these to the notes that you have on the previous page of your packet and seeing, does it fit into one of those properties. Okay, and we'll come back and discuss 4 of each. So we'll just go through these one at a time. This first one has addition on the inside turning into addition on the outside. We kind of talked about this. What does addition on the inside translate to? No. What does it translate into? Nothing. Addition on the inside doesn't. Now you're linking addition with multiplication. That's good, but it only works one way. Okay. Actually, we see that happen somewhere in here. Where do we have multiplication on the inside turning into addition on the outside? Number 3. Yeah, totally. So this one is correct. This was in our true column, I hope. How about number 2? We got multiplication on the inside, and then they just brought the coefficient to the outside. Is that how that works? Coefficient inside becomes a coefficient outside. That doesn't work either. I'm sorry. Coefficient on the inside turns into a coefficient on the outside. Is that how that works? What turns into a coefficient on the outside? Exponent on the inside. Give me an example of a problem where we've got exponent on the inside turning into a coefficient on the outside. Number 6. So number 6 goes in the true category, but number 2 is false. We already talked about number 3. How about number 4? We got division on the inside translating into subtraction on the outside. Yep, that's how that works. Division on the inside turning into division on the outside. No, that's false. We talked about number 6 being true. How about number 7? That's false. We could make it true if we put parentheses around the log x with the 2 on the outside of the parentheses. That would make it true. So if that power of 2 was on the entire log x, not just on the x, then it would be true. And this last one, what do you think? Well, we said it was 4 and 4, right? So by process of elimination, it has to be true. Why are they putting these absolute value things around here? And why did they not put the absolute value on the 4 out here? I guess it's not really necessary in a 4 because this absolute value of 4 is 4, right? They kind of just evaluated it. We don't know what x is. Now this would be interesting. This would be an interesting question for the test. What would the domain of this equation be? Log of absolute value of 4x. Would it be everything now? What are we not allowed to take the log of? Can't take the law of negatives. Are we going to ever end up with a negative inside of this log, no matter what x is? Except there's one other thing we're not allowed to take the log of. 0. Is there a way we could end up with a 0 in here? Yeah, so the domain of this would be everything, all real numbers except for 0. All right, you guys did awesome on that. We got one more thing to do. You'll want your calculator out for this. So there's this thing called the change of base formula, and I need you to know it. Every year I get the question, why do I need to know this? My calculator does this already. And there's a very good answer for that, which I'm going to try to explain in a minute. But let me try and explain why people ask that question. We're going to do example 5a together right now. Go ahead. That's fine. I appreciate you. And I'm going to show you how to do it with your calculator, okay? Some of you will be able to do this with your calculator and some of you not, okay? It depends on how new your calculator is. Mine does not actually, but I'll borrow one of yours here in a moment when I find out who this does work for. Could you guys go in your calculator and hit the math button and scroll down and see if you can find me an option that says log base. Log base. If you've got one of the yellow school calculators, yours is not going to have it. TI-83s I don't think are going to have a log base on them. Who's seeing log base? Are you seeing a log base on yours? Okay, That's excellent. Did you try hitting the button and see what it does? Try hitting enter on log base to see if you can figure out what it does. That's pretty cool, isn't it? Can I borrow someone's calculator that has a log base just so I can put it up on the screen? Thank you. So some of us are going to get a little jealous here because we're going to be like, oh, I wish my calculator had that. But don't get jealous, okay? All right, so check this out. So their math has more options than our math. See how it's got, let's look at this. It's got piecewise, numeric solver. Go to log base and check that out. Isn't that cool? It lets you put the base in. Oh my gosh. And the argument in there and hit enter. Oh my gosh. It'll evaluate it for you just like that. Now, my calculator doesn't have that. So I can do logs on my calculator, but I can only do certain bases. What bases can I do on my calculator? I can do log base 10. That's this button right here. And what other base can I do? I can do log base E, which is the LN button here, right? So, but you guys can do all the log bases. It actually turns out that all of us can do all of the log bases if we know this thing called the change of base formula. And you need to know it even if your calculator does it, okay? So please do not ignore this just because your calculator's got the fancy button. In fact, I'm gonna prove it to you right now. Somebody who all's got the log base? Okay, so we're gonna do a race on part B. Now you need to start with a clear calculator, okay, clear screen. We're gonna type in the log base 6 of 10. I'm gonna do it on my calculator, and you guys are gonna do it on your calculator. And I'm gonna be faster. Fair warning. I'm gonna beat you to it. Okay. So not only can I do it, but I can do it faster than you. Are you clear? You ready? Okay, someone want to give us a 1, 2, 3, go?
3, 2, 1, go.
Oops, I typed it in wrong, sorry. All right, maybe I won't get it this time. There we go. Boy, I blew that. I would have gotten it. I typed in the wrong problem. I mixed and matched. Are you getting the same answer that I did? 1.28 something 509? Okay, so there's a way to do this using the change of base formula, but I need you to hear this, okay? This is the part I don't want you to miss. Change of base formula does more for us than just allow us to put fancy logs into our calculator. A lot more, okay? So you're going to use this next year in calc. We're going to use this actually on Wednesday when we're solving equations. So whether or not your calculator does this is irrelevant. You need to know the change of base formula and how it works. So the change of base formula basically says, if I have a log base b of x, I can evaluate that using any log base that I want. Any log base that I want, no matter what. I could use a common log, which is what I just did in my calculator a second ago. And what I would type into my calculator would be the log of x divided by the log of your base. But I could also do it using a log base e, a natural log. Same idea. Oops, they need to match though. Okay, but I want you to write down one more thing too. We could also do it using the log base, I don't know, 42 is my favorite number. So this is called the change of base formula because if I end up getting an answer that's in base 3, for example, like example A here, I can change that into a log with any base that I want. Base 10, base E, base 42, base pi, I don't know. And why would I ever want to do that? Well, because maybe I've got something else in my problem that's got a log in a different base, and I want them to match so I can start putting things together. So as long I can turn this into anything that I want. Now we most commonly do it on the calculator using log and ln. In your assignment, they're going to ask you to express it using log and ln because that's what's on your calculator. But let's go ahead and do this the long way, okay? It's not longer, it's actually quicker. Could you guys first write down the log of 16 over the log of 3 and then type that into your calculator? And let's write down, we'll go to the nearest thousandth. That's 3 decimal places. Log 16 divided by log 3. 2.524. All right, now be prepared to be amazed because I want you to also write down ln 16 over ln 3 and type that into your calculator as well. And oh my gosh, it is the exact same thing, isn't it? What? That's crazy. It's almost like the log that we chose did not matter. Okay, so in your assignment, they're going to give you some problems that are going to look like this, and it's going to say rewrite this using only common logs. Common logs are the ones that are just log with no base written. And then there'll be another group of problems where they'll say rewrite it using only natural logs. So you're just going to write one of these two things depending on what the instructions say, and then write down what your answer is and move on with life. Okay? So go ahead and do the next two. If I were going to write this using only common logs, your choice. You don't have to do both if you don't want to. This is what I meant to type into my calculator when I raced you a minute ago. Totally would have won, by the way, if I typed the right thing in. If you haven't typed part C into your calculator, I challenge you to try and think of what the answer is without using your calculator. That's what it would look like if I use change of base formula with ln. We could replace those with logs if you want. But can you evaluate this without a calculator? Remember, a log is an exponent. What is the exponent? You put onto a base of 1/2 to make it equal to 2. What exponent would you put onto a 1/2 to make it equal to 2? -1. And you can try it in your calculator. That's what you get. I need you to know how to do this because I'm going to ask you specifically to do it on the test, and because with the work that we're going to do on Wednesday, you're going to be solving equations, and you're going to get an answer that looks like this. X equals the log of 8 divided by the log of 2. And I am here to tell you right now that answer would be unacceptable for full credit on a test. Because we can change that into what? What is log 8 divided by log 2? Can you write that as a single log? What's my base? Log is 2. Log base 2 of 8. That's what that's equal to, right? That's the change of base formula, but in reverse. And I would expect you to know what the log base 2 of 8 is. Yes, it is. Yes. What is the exponent you would put onto a base of 2 to make it equal to 8? 3. Okay. So log 8 over log 2. I need you to see that and think, ooh, that looks like the change of base formula. I'll change it into a base of 2 and see if I can evaluate that. So you'll practice these a little bit in your assignment. I just don't want anybody thinking, because I had several people last year that were like, I'm not going to bother learning that because my calculator will do it for me. I need you to know how to use this change of base thing. Okay? All right, does anybody have any questions? That's it for today. Hey, I just want to give you a heads up on what we're going to do next time. This lesson that we're going to be doing, this is going to be awesome timing because this is probably the most challenging one of the whole unit. And I get to get observed trying to teach you guys how to solve equations, which is pretty much impossible for someone to teach you how to do this, because this is one of those things you got to kind of just like, you got to try and fail. It's kind of like learning how to do proofs, okay? So there's lots of different ways to do it. We're going to kind of struggle our way through a few things. You're probably going to walk out of here. Chances are, there's a good chance you might walk out of here on Wednesday thinking, like, I don't feel like I know how to do that. Like, if I had to solve an equation, I don't know that I'd be able to pick which one of those things to do. And that's pretty much normal. Like, it's going to take some experience running through some different problems, trying some different things, and seeing what works. So I want to give you guys that heads up now. I'm going to tell you this again in front of our observer on Wednesday. But this is kind of, it's a little bit of a challenging thing. The cool thing is there's, for some of these equations, for a lot of them, there's multiple ways to do it. So, but we don't need to worry about that for right now. Once you guys start on your assignment, it's up on the board here. I just put it up on Canvas too. While you